In the last lecture, we discussed conjugate direction methods in general. And among the actual methods, we discussed one, which was Powell's conjugate direction method. Now, in this lecture, we will discuss another conjugate direction method, which takes the help of the gradient to develop the direction. And that is why it is called conjugate gradient method. The direction is not along the gradient or opposite it, but it plays a role in deciding the direction. So first we will develop the method on a quadratic function. Then we will see how, in this case, the subspace expansion works with addition of new conjugate directions. And then we will see how the method operates on general functions. So to begin with, we take this convex quadratic function, positive definite A, and from any point we start. The first direction is the negative gradient direction. Then there is a line search and update as usual, and the update happens to be this, okay, alpha k, for which we have developed the formula already, okay, and subsequent directions are worked out by adding a component of just the previous direction to the present negative gradient. So at xk plus 1, we want dk plus 1, and for that we take the gradient at xk plus 1, negative of it, and with that add a component of the just concluded direction. So it is not negative gradient. And this beta k here, how much component of the previous direction has to be added, that comes out from this formula, which is quite obvious actually. And this sequence in n iterations will converge to the solutions for a quadratic problem. Now, this conjugate gradient method, which has these steps in the operation, is called conjugate gradient because it is a conjugate direction method that works with the help of the gradient. Now, you would, if you look at these a little carefully, very soon you will notice that there is nothing dramatic in this. Okay. Every step is quite reasonable. So, for example, the first step, in the absence of any history, no direction which has any record till now, negative gradient is a reasonable choice. Okay. Then this is a line search, nothing very specific. And this is the result of the line search that we analytically found earlier. Okay. So which you get by setting this condition. And the only decision as such is to add a component of just the previous direction to the negative gradient. Okay. Now the formula for beta k is nothing very surprising because you want this new direction to be conjugate to the old direction. Okay. Dk. So the moment you say that dk plus 1 and dk are conjugate, then how do you impose that condition? You multiply both sides with the matrix A and then take the inner product with dk, and then here you have got dk transpose A dk plus 1, which you set equal to 0. Then from here, then you will get minus grad f xk plus 1 transpose A dk, and that is here. Okay. So minus sign. So taking it on the other side of the equality, minus sign will go. So this is here. And from this, you will get beta k times dk transpose A dk, which has gone here to give you beta k. So this is the formula for beta k, which is nothing. So everything is very reasonable step, nothing very intelligent or something very great that way. So everything looks reasonable. What is really surprising out of this set of reasonable steps is the claim that dk plus 1 is not only conjugate to dk, which we have forced by this beta k formula, but it is conjugate to all the old directions also. This is something really deep. So let us see how it works. So for seeing the working of the subspace expansion, we will denote three subspaces of the solution space. Okay. And there, basically not the solution space, the difference space or rate space, but it amounts to the same thing. In Rn, we will talk about three subspaces: direction space dk, gradient space gk, power space pk. Okay. And they are defined like this. And for this discussion, where we have to write and speak many times of grad f at xk, we would rather use the notation gk for this discussion. Okay. So the direction space is the set of directions till now traversed. Gradient space is the space of the subspace spanned by the gradients, k of them. This is also k of them. And power space is basically this first original gradient g0, then that multiplied with a, that multiplied with a square, up to that multiplied by a to the power k minus 1. This is also k members. Okay. So till k iterations, you will have these many members in each of the subspaces that we are talking about. And the claim is that as the algorithm proceeds, k starting from 0, 1, 2, 3, 4, these three subspaces grow together, such that for every iteration, at every iteration, this subspace, and this subspace, all three are identical. Okay. And each direction is conjugate to the previous ones, all the previous ones, till you get a gradient which is 0. When this process stops, it cannot go forward, and that many you have the set. Okay. So if the gradient delays as much as it can to become 0, even then in n steps it has to become 0 for a quadratic function. Okay. Because more than n conjugate directions you cannot get. So for k equal to 1, from the starting decision d0 being minus d0, it is very clear that these three subspaces are same, because this one ends here, this one ends here, and this one also ends here, because k is 0. So a to the power k minus 1 doesn't make sense. Actually, k is not 0, k is 1. So, but still, a to the power 0 g0, which is simply g0. So all three are obviously same for k equal to 1. And the other part of the proposition, that each direction is conjugate to all the old directions, there is no direction in hand. Right now, only d0 is the direction. So there is no old direction to talk about. So the question of conjugacy does not arise. As we proceed, the entire dynamics of the method will be driven by just these 2 points. The update formula, this, which immediately gives the gradient difference formula, that is gradient here is equal to gradient here plus a times this vector. Okay. So this we will be using again and again, and the direction update formula, which is this. Okay. So basically these two update formulae, this is in the background of this, drives the entire algorithm and its progress. Let us see how. So for k equal to 1 we have seen. Now let us see quickly k equal to 2. Okay. For that, the gradient update formula is this, and d0 was originally selected as minus d0, so this, and d1 from the direction update formula is this, which can be expressed as this or this also. Why? Because d0 is minus d0. Okay, so basically that is minus beta 0 g0, that is minus beta 0 g0, and from that you have to subtract minus g1 and subtract g1, that is you have to add minus g1, so the negative of this, so another minus 1 times g0 will come, which is also here. What else will come? Minus minus plus alpha 0 a g0, that is this. The same thing can be written also as this by writing this part minus d0 as d0. Okay, so you can write it this way or this way. Now why we are writing it to almost same way, equivalent, that will become very clear soon. From this first one, it comes out that g1 is a linear combination of g0 and a times g0. Okay, coefficient here is 1, coefficient here is minus alpha 0. So therefore g1 belongs to this subspace, which is P2, the power space for k equal to 2. Since D1 is also a linear combination of G0 and AG0, so D1 is also in this same space. So G1, D1 both are in this space. Okay, P2. Now we already know that for k equal to 1, the three spaces were identical, which we have seen earlier. And therefore, that means basically that, see, P2 actually includes P1, and therefore this whatever. So D0 and G0 were already in this because they were in P1 itself. So G0, G1, D0, D1, all of these are in P2. And D0, D1 constitute this, G0, G1 constitute this. Okay. So therefore, these spaces are entirely contained in P2. Okay. The same identities above can be viewed in another way. From here, if you, last time we read G1 as a linear combination of these two guys. If we take G0 on the other side, then you can also say that AG0 is a linear combination of G0 and G1. Okay, G0 here, G1 here, taking G0 on the other side. So since AG0 is a linear combination of G0, G1, which is this, so AG0 is a member in G2. Okay? And G0 was already a member of G1, so also in G2, because G2 is a superset of G1, a bigger space. Okay. And similarly, by looking at the second one, taking D0 on this side, D0 term on this side, AG0 can be seen as a linear combination of D0 and D1, which is this capital D2. Okay. So therefore, AG0 is in capital D2 also. So AG0 is in capital G2 as well as in capital D2. And G0 was already in G1, which was same as D1. And therefore, in the superset G2 or D2 also, they will be there. So that means both the basis vectors of P2, that is G0 and AG0, both of them are contained in this and this. And therefore, P2 is also a subset of G2, P2 is also a subset of G2. Now, when you have this situation that A is a subset of B and B is a subset of A, then you know that they are equal. That is, it's not a proper subset. Neither is this a proper subset. So they are equal. So P equal to G2 and P equal to D2. So you have this. So for K equal to 2 also, the subspaces are identical. Okay. Conjugacy of D1 and D2 follows from beta 0, because based on that we have actually worked out D1, this formula. On this formula we actually forced conjugacy of D0 and D1. By that only we determined beta 0. So from the formula for beta 0, these two are conjugate. That is trivial. So the proposition is true for K equal to 2. Now how this is working, you will get a better feel if you work out a step like this on your own. So my prescription is that work out the arguments, similar arguments at one higher level to establish the proposition for K equal to 3 to appreciate its sense properly. But for the actual proof, you don't need that, because for the trivial cases, K equal to 1 and K equal to 2, we have already shown. Based on this seed, we can actually continue with the main induction argument. The trivial cases have been already established. So now we say that suppose the proposition is true for K equal to J. That means Dj, Gj, Pj, each of dimension J, they are all equal. And the directions till now in Dj are mutually conjugate. Okay. I mean, in Dj I'm telling, but they will be in Gj and Pj also. But in Gj, these are the directions which describe Dj. Okay. These are the vectors which describe Dj. Okay. So these are all conjugate. This much we assume as the induction hypothesis for K equal to J. And we try to look for arguments to show that the proposition is true for K equal to J plus 1 also. Okay. So after J iterations, the algorithm reaches Xj, minimizing the function over the subspace Dj. Therefore, the gradient at Xj, Gj, is orthogonal to the entire subspace Dj. Okay. And since Dj minus 1 was in Dj, which means in Pj also, which were same, okay, we have taken it here. So A times that will be in Pj union. Whatever happens, if you multiply the vectors in this subspace with A, you see Pj had G0, A G0, A square G0, A cube G0, up to A to the power J minus 1 G0. If you multiply that with A, then all these will be there, and one more vector will come, that is A to the power J times G0. So if you take one more vector like this and its span all vectors along that direction, with that if you take the union of Pj, basically in Pj whatever is there, you add one more direction. That direction is the direction of this. Then that is Pj plus 1. So you find that A times Dj minus 1 is in not in Pj but in Pj plus 1. Okay. And Dj minus 1 was already in Pj. So this thing, A times Dj minus 1 is in Pj plus 1. The gradient J minus 1, the previous one, was already in Pj, which is a subset of Pj plus 1. So it will be in Pj plus 1 also. So that shows that this term and this term both are members of Pj plus 1. Okay. And therefore, this linear combination of Gj minus 1 and A times Dj minus 1, that linear combination also will be in Pj plus 1. Okay. And Pj, Gj were already same. Okay. So all the other elements of Gj, that is G0, G1, G2 up to Ga minus 1, Gj minus 1. All of them were already in this. So already, and this also. So that means that if you now get that Gj also is contained in this, then together Gj plus 1 will be a subset of this. But it cannot be a proper subset because Gj was in Dj minus, Gj is in the next space, okay, but it was not in Dj, okay. It was in perpendicular to Dj, okay. Gj was perpendicular to Dj. That is, this gradient at xj was perpendicular to the direction set Dj, okay, that subspace. So that means it cannot be in Dj, okay, and so it was not in Pj either because Dj Pj were same at that level, okay. So that means that this newcomer, the next gradient that you have got, in order to accommodate that, this new member of Pj plus 1 had to be used, okay. So for whatever purpose to accommodate this, this was to be used. So using that, one can accommodate this in the capital Gj union this gradient, new gradient that has come, okay. So that means that Aj times G0 is in this union, which is capital Gj plus 1. So at this level, for j plus 1 also, you find that the two subspaces are same. By similar arguments, you find this equality also of the subspaces D and G. See, Gj is in Pj plus 1 and Dj minus 1 was in Dj already, which means in Gj also, which means in Gj plus 1 also. Okay. Now, this new direction, Dj, is a linear combination of the new gradient plus the old direction. Okay. So, both parts, this is already in P plus 1, and this is also in G plus 1, which means, yeah, which means at P plus 1 because this equality we have already established. Okay, so combining that with the equality of the previous subspaces, we get that the new two subspaces are like this. That is, all directions till now are in this. The last one, which is the newest addition, was not in Gj, but it is in Gj plus 1. Okay. So, but it cannot be a proper subset because Dj was not in Gj. Fine. So therefore, the two are equal. So summing up all together, you find that all the three are same for k equal to j plus 1 also. And finally, for the conjugacy, mutual conjugacy, you try to evaluate this di transpose A dj and put in the formula for dj here, minus dj plus beta j minus 1 A dj minus 1. Now for I equal to j minus 1, the last I that you can talk of for this, the biggest I that you can talk of in this purpose, for I equal to j minus 1, if you put it here, then, and if you put it here, then the formula for beta j minus 1 tells you that this is 0, because formula for beta j minus 1 is essentially remove the minus sign of this thing divided by this thing. Yeah? So this is 0 from the formula of beta j minus 1. For I less than j minus 1, the first term is 0 because of the induction hypothesis. Okay. First part, that Gj is orthogonal to all the old directions. Okay. or you can say that di was already contained in dj minus 1, which is the same as pj minus 1. So if you multiply it with a, then it will be in pj. Okay, so a di is in pj, and pj is same as dj. Okay, so the gradient is orthogonal to all of these. Okay, while the second is 0 because of the second part of the assumption in the induction hypothesis that all the old directions are already conjugate. So that is for j I less than j minus 1. For I equal to j minus 1, we have already settled. So you do not have any problem here. Okay. So this shows you that di transpose a dj for the new direction dj, all the previous directions are mutually conjugate. For the previous one, the induction hypothesis told us that, so we could use that here. Okay, up to dj minus 1 and I less than j minus 1. The induction hypothesis still told us this, and for the new one, we have got the beta j minus 1 formula, which gives us the conjugacy of this for the new one also. So altogether, we get that these three are same, spanning a subspace of j plus 1 dimensions now, with all the vectors in dj, that is d0, d1, d2 up to dj being mutually conjugate. And the proposition is true for k equal to j plus 1. So by induction argument, you say that the proposition will be true for all k till either k equal to n, when it will be forced that gradient will be 0, or gradient turns out to be 0 even before that. Then also it will end, the method will end, and there will be no more possibility of the subspace expansion. Okay. Now we explore how we apply this on general functions, which are not necessarily quadratic and not necessarily convex everywhere. Near the minimum point, around the minimum point, it will be convex, but far away it need not be. But the iterations will go through far away locations also. So first thing, so for that, we try to work out some alternative formulae for the alpha k, beta k, the two scalar coefficients that we need. So that will help in the general functions. But to formulate them, we try to work out on the basis of quadratic functions only, such that their interpretation remains the same. Say the inner product of this direction formula with grad f will give you this. Grad f transpose dk equal to minus grad f transpose grad f at xk, basically square of the norm. Okay, and this part will be 0 because grad f xk transpose dk minus 1, this is 0 because you reach xk by a line search along dk minus 1. So the gradient there where you have reached through a line search must be orthogonal to the current direction of line search, otherwise the line search would not stop there. So this is 0. So in the inner product, the second term will have no contribution. This first term is this. Okay, and make note that this is negative. Okay, because this is minus grad f xk mod square. Okay. And that actually in the side also tells you that dk is a descent direction. Then the original formula of alpha k that we saw trivially, in that we can put this thing, okay, minus gradient transpose gradient. So this minus and this minus go off, and in place of this you have got this symmetric kind of formula. Only gradient above and only this below. Okay. From the above, you basically replaced this minus dk with grad fk in the inner product. That works out all right because of this. This is the alternative formula for alpha k, which will be quickly used. Now, we already know that the gradient difference between two successive points is a times the step, that is alpha k a dk. Okay. So this beta k, which was originally evaluated like this, in place of this a dk, we can put this gradient difference by alpha k. So in place of a dk, we put this gradient difference by alpha k, and this denominator remains in the denominator. So this beta k, in this, the denominator we try to get rid of it by considering this alpha k times dk transpose a dk, that is in the denominator. So there we put this. Okay. So this we know as the famous polar Riviere formula. Okay. For the direction update. In the direction update, beta k is the only thing that you have to really evaluate. And for that, rather than this formula, now we have a simple straightforward formula which operates only on gradients. Gradients at xk and xk plus 1. Okay. Now, quickly, we will find another even more simpler formula for beta k, so far as it looks. Okay. I mean, that is really simpler compared to this, by considering that this grad f xk plus 1 transpose grad f xk is actually 0. So if you open it out, only the first term will contribute and not the second term. Okay. So see this inner product. Okay. Grad f at xk plus 1 transpose grad f at xk. So now two rounds of opening one by one. Okay. This grad f at xk, for that we can write this, because the direction update formula was dk equal to minus this gradient plus this. So you take that gradient on the other side, dk on this side. So gradient fxk will turn out to be this. Okay. And now try to open it out. First of all, the first inner product, grad f at xk plus 1 transpose dk, that is 0. Because along dk you conduct a line search to reach xk plus 1. So that is 0. Only one term will remain. Beta k minus 1 times this gradient into dk minus 1. Okay. So in this step, we opened this gradient. Now you open this gradient by the similar formula. Gradient at xk plus 1 is gradient at xk plus a times the step in between. Put that here. And now open this out. So as you open this out, you get grad f xk transpose dk minus 1, this, plus alpha k times dk transpose a dk minus 1. Both are 0. This is because the line search along dk minus 1 concluded at fxk. So the gradient there is orthogonal to this. So this is 0. And this is 0 because the two successive directions are conjugate. Okay? So both of them are 0. So that means this term entirely is actually 0. Okay. So when you open this transpose this is 0. So in the numerator, what remains is only this transpose this, same thing. And that gives the alternative formula for beta k, which is given by Fletcher and Reeves. So Fletcher-Reeves formula. This looks better, right? It looks very symmetric. Above it is the mod square of the current gradient, and below it is the mod square of the previous gradient. That's it. Okay. So both of these formulae are actually equivalent for a quadratic function. But for a general function also both are equally good, you can say. Okay, because both actually have come from the same source. But for general functions where a is not constant and things don't work out exactly as the quadratic function. So there will be small difference of the values of beta k that will come out. Okay. So, and note that both the formulae are free from the Hessian matrix, and that is very important. That is all the reason of our exercise here to work out alternative formulae for beta k. Because in general functions, general problems, in actual implementation, actual application, Hessian will not be constant. So you will not have a matrix called A. And whatever the matrix is, variable as it may be, it will not be known to us because we do not determine Hessian. Okay. So the entire operation will be carried out by only using gradients, gradients, gradients everywhere. And the new beta k formulas, whether it is Fletcher-Riggs formula, this, or the previous Pola-Criviere formula, both are based on only gradients. Okay. Now this looks a little more symmetric, simpler, and more elegant compared to Pola-Criviere, but in actual implementation, the Pola-Criviere formula actually has a slight advantage in a particular context, which we will see. Okay, but both are quite used. Now, the formula for beta k has been freed from the Hessian matrix A, which keeps on changing, and we don't know it. But the formula for alpha k still has A, okay, and that is bad. We don't like it. So, in the denominator, you have dk transpose A dk. Okay, so there that A is still sitting in the formula for alpha k. But we will not use the formula for alpha k because we will conduct the actual line search. Okay. So for alpha k, also you don't need the formula because you conduct a line search. And for beta k, you use one of these formulae, Fletcher-Riggs or Pola-Criviere, which doesn't talk about the Hessian matrix A. It talks about only gradients which we have evaluated. Okay. So this way, the algorithm gets generalized for general functions, for general problems. Now you see the algorithm. Select a gradient tolerance and a tolerance on directions. Okay. Directions being linearly independent or dependent on that tolerance. That is how much linear dependence you are ready to tolerate. We will come to that. And the starting solution, x0, evaluate the function value and gradient, set the iteration index and find out the initial direction, which will not come from the formula. Okay, because formula is for subsequent directions. The initial direction is just negative gradient. Now the iterations start actually. Initially for k equal to 0, next k equal to 1, 2, 3, 4. So line search and update. Fine. At the updated point, you evaluate the function and the gradient. If the gradient turns out to be too small, that means you have converged. Stop. Otherwise, you need the next direction. So for that, find out beta, either by the Pola-Criviere formula or by the Fletcher-Riggs formula, and therefore get the next direction as we have discussed. Now, here a little issue comes sometimes that if the next direction turns out to be very much like the old direction only, just the previous direction, then even though nominally conjugate, uh, they turn out to be linearly dependent. And the new search is not going to give you much help because the old search along dk has concluded at xk plus 1. And if the dk plus 1 direction is also going to be more or less along dk only, just 2 degrees or 5 degrees away, then at that small angle, the new search will stop very soon. Okay. So then basically it will not move. It will not move much if the angle is too less. So you try to find out if the angle is too less. So between two vectors, how do you find the angle? You say that take the inner product, dot product of the two vectors, divide that by their magnitudes. So this turns out to be cos theta. You don't need theta, you don't need it in degrees or radians. Cos theta will do. Okay. If they are too close in direction, then the angle will be small. Okay. So angle will be small means cos theta will be close to, you know, having magnitude 1. It can never go beyond 1 because cosine never goes above 1. So if you check that 1 minus cos theta, if that is very small, that means that cos theta magnitude is very close to 1, which is bad. Okay. It would be lovely if the cos theta magnitude is small. Okay. Around 0. That means there is a good angle between them, 75 degrees or 80 degrees or like that, or 60 degrees. Okay. So 1 minus cos theta is what is here. If that turns out to be too small, that means that the two directions are almost same. In that case, what has happened through all these iterations is that the directions have become stale. Okay, no fresh direction is coming, and that means that you restart. Okay, whatever is the current iterate, now call it the initial solution and start all the way here, as if from here you are starting conjugate gradient algorithm. This is done if the new algorithm, new direction turns out to be extremely dependent on the old one. Okay. Otherwise, in most iterations, this will not happen. Okay. So otherwise, increment the index and continue with step 3. That is the next iterate without restart. Continue. Okay. So this is the conjugate gradient algorithm. It's quite fine algorithm. It works. However, except for this problem which arises sometimes for which you restart. Okay. Now, on general functions, talking about performances. The Hessian of general functions varying over iterations, there is a question on the sense of the conjugacy. What is this conjugacy? I mean, with respect to what matrix these directions are supposed to be conjugate? This is a question which has a loose answer. Okay. So you say that the directions generated are loosely conjugate with respect to some local representative Hessian. That also we don't know. Okay. So local bunches of close by directions over which last 4 iterations have been conducted, they are roughly conjugate with respect to a Hessian approximation in the local neighborhood. Okay. So towards the end, when the steps of every iteration, steps of the iterations turn out to be small size, then this loose conjugacy will turn out to be accurate conjugacy with respect to the local Hessian, which is more or less constant over several steps. And because of this, the algorithm in general will not converge in any iterations. It will continue. And that is why the algorithm, the way it is written, continues. Okay, it doesn't stop after any iterations. Now, after n steps, the algorithm presented in the previous slide was with the sense of continuing as usual. Okay, but some authors also suggested early that after n iterations, continue with a fresh cycle, but there is no need. We continue only when we restart, only when there is a breakdown of the direction developing mechanism, when the new direction turns out to be linearly dependent on the old one, then only we restart. Otherwise we keep on continuing as if nothing has happened. Okay, so the boundary of an iteration getting completed is nothing very special. Okay? You continue, except when things go wrong with the direction generating mechanism, then you say that the current iterate, we call it x0 and start afresh. Okay, that means that now the negative gradient only will be the next direction. Now we discussed once that the Pollack-Riviere formula has a marginal advantage over the Fletcher-Dietz formula. In what way? In what sense? Because Pollack-Riviere formula has some immunity to this discontinuous and violent restarts. before the restart situation arises, it naturally takes some measures. Okay, we'll see how. And therefore, the discontinuous restart situation occurs very rarely in the case of polar Previer formula, not in the Fletcher Rees. Let us see how. Say, suppose epsilon d is something like 0.05. Okay? So, even before this goes below 0.05, okay, even when it is something like 0.06, 0.055, 0.052, something of this new direction being most dependent on the old direction will happen, right? So when that will happen? When the component of this, see, these two vectors composing dk plus 1 are orthogonal, but it may happen that you go westward 2 kilometers and then north by only a few steps. Then most of your direction will be west. Okay, so that means that this component dominates this sum so much that the next direction will be almost like the same as the previous direction. Okay, now if you are using polar Riviere formula rather than Fletcher Rees, which happen to be more good looking formula, okay, but if you are using this bad looking formula, relatively bad looking formula, then what will happen? Suppose epsilon d is 0.05. Till now it has not gone that bad, it is till now 0.06, but with 0.06 beta k, I mean 0.06, I mean that much closeness to linear dependence itself, dk plus 1 is to an extent overwhelmed with dk. This doesn't have much say in that. Then what will happen? The worst that can happen is that in this step the line search will not achieve much. So wherever was xk plus 1, the next one xk plus 2 will be quite close by. Okay, so for the next iteration there will be xk and xk plus 1. Okay, so if in the next step xk plus 1 happens to be very close to xk, because the new direction being very much like the old direction, alpha k turned out to be very small, because in the previous iteration most of the important alpha k was already covered. So this means that xk plus 1 and xk will be very close, and therefore their gradients also will be very close. And Pollack-Riviere formula is partly driven by the difference of the two successive gradients. So if the line search does not achieve much, which is the harbinger of this trouble, before this trouble comes, for one iteration, two iterations, this will turn out to be small. Okay, at least one iteration, basically one iteration. So this turns out to be small. Then in the next round, beta k will turn out to be low. Okay, so in the next round, if beta k turns out to be low, that means the fellow which was dominating, that has been put down, and then this will play its role properly, and therefore the next direction can be expected to be good. Okay, so before the threshold is crossed, this driving by the difference of gradients handles the issue in such a way that very smoothly next round beta k turns out to be low and this kind of situation does not arise. So such violent discontinuous restarts will be less often for polar Previer formula. This is the actual advantage, which you will see only in the general functions, not in the quadratic functions, because for quadratic functions both formulae are equivalent. Okay. So let us quickly check the convergence properties. This we have already seen, that the inner product between dk and the gradient at xk is negative, and that shows it is a descent direction. And then along this descent direction, you conduct a line search to get xk plus 1. That means at xk plus 1, function value is certainly going to be smaller than fxk, even by a little if it is smaller. So the global convergence is assured. Now talk about local convergence. A conjugate gradient step is at least as good as a steepest descent step. because the negative gradient is a component in the direction choosing mechanism. Mostly better, and rarely worse when the new direction is almost the same as the previous direction, but that is very rare. So, and it approaches Newton's step very close to the optimum point. Okay. The rate of convergence of conjugate gradient method is thus better than steepest descent method and less than Newton's method. So it is called superlinear. Now, how good is conjugate gradient method against its competitors? The closest competitors are Powell's method, which we studied earlier, and quasi-Newton method, which we will study next. Now, so far as efficiency and efficacy is concerned, conjugate gradient method falls between the two. Okay. However, on one count, conjugate gradient method is better than both of them, because quasi-Newton method has to, which we will see, quasi-Newton method has to store a matrix, okay, of dimension n by n, which is a lot of storage in large problems. Powell's direction set method also has to store the direction set, which means n vectors. Now, n vectors of n dimension actually basically means equivalent to a matrix of n by n size. So the storage is high for Powell's method. In comparison, conjugate gradient method operates only with vectors, only gradients and directions, nothing else. Okay. So this way, for large problems, conjugate gradient method has an advantage in both. However, has an advantage compared to both. However, Powell's method has an advantage when the function is not differentiable. Okay, because both conjugate gradient and quasi-Newton methods operate with first derivatives. Powell's method uses no derivative at all. So there Powell's method has an advantage. And we will see in the next round, next lecture, that quasi-Newton method has an advantage over both regarding efficacy and efficiency. Quasi-Newton method is the method for unconstrained optimization. Okay. But conjugate gradient method has an advantage even over that for large problems where the storage is an issue, memory is an issue. So to summarize our points of this lecture, conjugate gradient method generates new search directions by adding a component along the previous direction to the negative gradient at the current point. This is the spirit of conjugate gradient method. Every new direction so generated is conjugate to previous directions up to n minus 1 of the previous directions. Because more than n directions, you cannot have conjugate in an n dimension space. Now, it is one of the best methods of multivariate optimization and has special advantage on large number of variables. Okay? Because it operates with only vectors, while competing methods often work with matrices. So big storage. Even the simplex method, that also stores so many points, right? N plus 1 points make a simplex. So n plus 1 multivariate points will mean n times n plus 1, lot of storage, right? So even compared to that, conjugate gradient method has an advantage so far as storage is concerned. Okay. So here we stop, and in the next lecture we study quasi-Newton methods, which is the ultimate method of unconstrained nonlinear optimization. And it has applications in constrained optimization as well, as all of the methods have for that matter to an extent.